Imagine taking a star the mass of our Sun and crushing it down until it fits into a sphere the size of the Earth. At that scale, a single teaspoon of stellar material would weigh several tons. And gravity doesn't stop pulling once the star shrinks. It is constantly trying to crush that immense mass even further. What stops it from collapsing isn't heat, and it isn't any normal physical pressure. The star is held up entirely by a strict rule in quantum mechanics called the Pauli exclusion principle. This diagram shows what happens when gravity squeezes matter that tightly. The electrons are forced into an ever-shrinking space. Because quantum law strictly forbids two electrons from occupying the exact same state at the same time, they generate a massive outward force, pushing back against the crush of gravity. Physicists call this electron degeneracy pressure. For most dying stars, this purely quantum refusal is enough. The outward pressure halts the collapse completely, leaving behind a perfectly stable, glowing core known as a white dwarf. But a rule is only as strong as the threshold it can withstand. What happens to an absolute law of the universe when you pile on enough mass to push it past its breaking point? There is a line where quantum mechanics gives out, and once a star crosses it, it cannot go back. In 1930, a 19-year-old physicist named Subrahmanyan Chandrasekhar boarded a ship in India bound for graduate studies in England. During the weeks-long voyage, he worked on a glaring mathematical flaw in how astronomers understood dying stars. The early equations for electron degeneracy pressure assumed electrons behaved classically, but inside a highly compressed stellar core, these particles move so fast that classical physics breaks down entirely. This chart maps out the difference. If you treat electrons classically, the outward pressure scales linearly with the density. But Chandrasekhar applies a relativity. As electrons approach the speed of light, their momentum and energy scale differently. The outward pressure they can generate flattens out, becoming dramatically weaker. Past exactly 1.4 solar masses, degeneracy pressure fails completely. A stable white dwarf cannot exist. There is no hidden safety net. Without that quantum pressure, and there is absolutely nothing to stop the star from collapsing under its own weight. Gravity wins, unconditionally. Sitting on a boat, a teenager had calculated the specific numerical threshold that dictates the fate of stellar cores, and that calculation put him on a direct collision course with the most powerful astronomers in the world. In January 1935, Chandrasekhar stood before the Royal Astronomical Society in London and presented his meticulously checked math to the establishment. Following his presentation, Arthur Eddington, one of the most eminent astrophysicists alive, took the stage. He publicly dismissed Chandrasekhar's result, calling it a reductio ad absurdum. Eddington was defending a deeply held, lifelong worldview. He carried a profound philosophical objection to physical singularities. He refused to accept that nature would ever allow a star to collapse indefinitely into what we now know as a black hole. He told the room there should be a law of nature to prevent a star from behaving in such an absurd way. The math was sound, and the world's leading quantum physicists knew it. Heavyweights like Niels Bohr, physicist Wolfgang Pauli, and theorist Paul Dirac privately acknowledged that Chandrasekhar's relativistic math was correct and Eddington's physics were wrong. Yet none of them spoke up in his defense at the time. Astronomy held a lower status among the physics disciplines in the 1930s, and openly contradicting an authority as revered as Eddington carried severe professional risk. The physical limit of a dying star resolved cleanly on paper. But the objective scientific method folded under the immense gravity of human hierarchy, stalling broader acceptance of the math for years. So what actually happens out in the universe when a stellar core crosses that unyielding 1.4 solar mass threshold? It produces two entirely different endings, depending on how the star arrives there. First, an existing white dwarf can slowly pull matter from an orbiting companion star. As it inches over the limit, the extreme conditions ignite runaway thermonuclear fusion, detonating the entire star nearly simultaneously. This creates a Type A supernova. Because these explosions trigger at the exact same mass threshold every single time, they release remarkably consistent peak brightness. Astronomers use them as cosmic standard candles to measure the precise expansion of the universe. The second outcome happens when a massive star reaches the end of its life, and its dying core is already heavier than 1.4 solar masses. In this case, electron degeneracy pressure is never enough. The core skips the stable white dwarf phase completely. It just keeps collapsing. The crush is eventually halted by an even more extreme force to form an ultra-dense neutron star. Or, if the mass is high enough, even that fails, leaving behind the exact black hole singularity that Eddington had so deeply feared. The exact same underlying quantum threshold is responsible for forging both the precise cosmic measuring sticks we use to map the universe and the most extreme, destructive objects physics allows. The universe ultimately played by Chandrasekhar's rules. Though it took nearly 50 years, he was eventually awarded the Nobel Prize in Physics for the limit he worked out as a teenager on a boat. The Chandrasekhar limit stands today as a load-bearing pillar of astrophysics. It is a perfect example of a threshold in nature that, once crossed, offers absolutely no path back. This video opens a 10-part series examining the line we can't uncross. Make sure to subscribe, because tomorrow, for day 142, we leave the stars behind and look at a runaway threshold crossed by a planet right next door. We're going to examine the real science behind why Venus cooked itself.
Thank you for sharing this moment of pure wonder. You are the true magic that fuels this journey. Until next time, remember to shine bright.